Okay, hello and welcome to my channel. Today we're gonna talk about the infinite square well in quantum mechanics. So first, let's take a look at how it is like. So the definition of it is that it is a potential of x that is zero in an interval. Here we'll take from 0 to a number a, and it is infinite elsewhere. When you draw it, it's gonna look something like this. This is your e of x. This goes to infinity. So the part outside here is completely irrelevant. This part is irrelevant. So you have something like this. You can already sort of imagine how your wave function would behave in a system like this. So first of all, here in the region where the potential is zero, your wave function is just gonna be like the free wave. But then when it is outside of this region, the potential is infinity, so your wave function is gonna get eliminated immediately, meaning it's gonna die down immediately. So from that, we can get our conditions. So first condition here, as I said, outside that region, your wave function is going to be zero. So your wave function, okay, so this is 0 to a. So if this is smaller than 0 or greater than a, these two would be 0. And the next one is the continuity condition that we mentioned before. So we see outside here is 0. Therefore, your wave function at 0 and your wave function at a has to be 0 as well. So this would satisfy the both conditions here, which is infinite potential, so this get pushed down immediately, and it has to be continuous. So these would be our continuity condition, and this would be just common sense when you look at the picture here. Alright, so when you have this, let's put our wave function into the time independent Schrodinger equation to get our eigenstates. So we put this in our time independent Schrodinger equation, get something like this. Wait, what? No. Oh yeah, right. I just be writing too fast because I don't know, man. I forgot. I have to go slowly. Is equal to that. From here, you put all those numbers on one side, and e. So just write e here is first region minus. Here you get that our second derivative here is equal to a minus k squared psi, and this would indicate that your wave function would take the form like this. So you learned this in math class, so I won't be mentioning any further information about this. You get your wave function psi to be the form c1 cosine kx plus c2 sine kx. Okay, now we have this. Okay, this is an eigenstate of x. So you have this. Now let's apply our conditions, our boundary condition to be more specific. So first one, let's take psi of 0 is equal to 0. Psi of 0 equal to 0. So what would that give us? 0 meaning the sine part is 0, so this part is gone. And 0 meaning this 1, so C1 times 1 equals 0. That would mean that C1 is equal to 0. And with C1 equal to 0, we can just ignore this part completely. So this is gone. Next is our psi at A is equal to 0. That would give us C2 sine kx equal to 0. Alright, so that is a number. Oh my god. It's Ka. I'm sorry. It's Ka. So we get that C2 sine Ka equal to 0. So what would give you the 0 in sine? You would want what inside here be a multiplet of pi, right? So I will erase this part. And let's continue. So you want your sine Ka here equal to 0. You would want the inside of your sine function to be a multiplet of pi. N is 1, 2, 3, and so on and so forth. Here you just get your k easily. N pi over a. Now you sub it back to your psi here. That would give you, see, I would just replace C2 with your normalization coefficient. So I will just write A sine n pi x over A. And there you go. This is the form of your energy eigenstates. Now we would like to find out what A is, right? So let's do that right now. So I'm gonna do this. You know how to do this. So that you pull the A out. The x, that guy is real. And pi x. I should put this in a bracket for it to be easier to see. And you can just put this in a calculator or something, I don't know. But you get that this is equal to, I think, 1/2 A. Yep, it is 1/2 A. From here, you just get, well, this has to be equal to 1 A. So from here, get that your A is root of 2 over A. Oh my gosh, I forgot to write here because the outside here is irrelevant. So you would only want to integrate from your region where the potential is 0, which is here 0 to A. That's how you get that. I forgot. Alright, so get your A here, and I'll rewrite your energy eigenstates. And X is, and this applies for every infinite potential, infinite square well. I'm sorry. There you go. So that would be the general form, and from here you can figure out the momentum and the energy. This part can be gone. In general, energy eigenvalue for infinite potential square well is, well, this can just derive it pretty easily. There we go. That is your general form for energy eigenvalues. And with the infinite potential square well, there would be a question that would ask you to graph the energy eigenstates. And I would like to do some demonstration for you to see. Okay, let's see which part I can erase. Okay, maybe this part. This part is good. Okay, I could just use that one. It was a little bit too far away from me, and I don't like that. Okay, let's draw another one. This is your v of x. Yeah. Okay. So how would you graph these energy eigenstates? So first, you gotta know the properties of the states first. So when you have an infinite square well potential, there would be two properties mainly. So first one is that it has no degeneracy in the energy, and the second is that when you have something like this, that which is the v of x would equal to the v of minus x, your energy eigenstates would either be odd or even. There is no in between that, and you'll see that right now. So let's graph our ground state. Okay, let me just draw some lines here. So ground state would look something like this with 0 nodes. So just GS with 0 nodes. Just like this. This is an even energy eigenstate. Next one, okay, I should drop this too. Just we're considering 0 to a, so this is a over 2. Okay, next, with your first excited state, your excite 1, that would be an odd state. There we go. Okay. And so on and so forth. That is an even state. 3, that is an odd state. Okay, my drawing is a bit bad. Yeah, this has 1 node, 2 nodes, and 3 nodes. So you can see some sort of pattern here. The node is going to increase from 0 to, well, to number, to integers number. And this would be even and odd states in between each other. So yeah, that's it. The infinite square well is not that complicated. So I guess that's it for today. Goodbye.